Let's start talking about sequences. So a sequence is simply a collection of numbers in a specific order. We can think of it as simply a list of numbers in an order. We may not know what that order is, but if we have a list of numbers, for example, 1, 2, 3, 4, that's a sequence. Now, for our intents and purposes, it's often helpful to think about sequences as functions. So what we have here is a sub n, and that's also known as the general term, and it's a way of generating any term in our sequence. So if I want to know what a sub 17 is, I would use the general term for a sub n. So in this particular case, in this example that I have here, I'm saying that a sub n is defined by 2 times whatever n is, where n is the set of positive real integers, or we can think of n as our order number, right? So this is just our order number. So we would say we would just take whatever ordered term we're trying to find, multiply it by 2, and add 1 to it. And again, what we're doing here is not that different from what we've done so far with functions. If I were to say something like f of x is equal to 2x plus 1. If I wanted to find the 17th term again, if I wanted to find the 17th term in this function or in this sequence, it would be equivalent to evaluating this function at 17, saying 2 times 17 plus 1, which would be 35. Okay? So n just simply tells us the location or the order of the term in the sequence. So let's do the same thing right now for this particular sequence. If I wanted to find, in this case, let me just go ahead and erase this so we don't get too confused. If I wanted to find the second term in our sequence, I would go, all right, well, what's 2 times 2 plus 1? Well, that would be equal to 5. If I wanted to find the third term in our sequence, 2 times 3 plus 1, well, that would be equal to 7. And this would be equal to 9. And so what we have here is this is what we say this is our a sub 1, this is our a sub 2, a sub 3, a sub 4, which is just another fancy way of saying it's our fourth term in our sequence. Okay? So thinking of sequences as functions will be really helpful for us as we move deeper into our study of what's going on with functions as we get closer to infinity. But before we get too ahead of ourselves, let's just practice writing the nth terms of sequences, which is another way of asking ourselves, what's happening to n to get to a sub n? So let's take a look at this first example. If I gave you this sequence, 1, 3, 5, 7, which looks really similar to what we just looked at, but if I gave you the sequence and I asked you to find a sub n, something that I always find helpful is to write the order terms right underneath or adjacent to these values. In other words, I'd say something like n is equal to, in this case, 1. This is when n is equal to 2, I get 3. When n is equal to 3, I get 5. When n is equal to 4, I get 7, right? So take a moment and just ask yourselves, what am I doing to n to get a sub n? Well, hopefully you had a chance to think about that. You would say a sub n is equal to 2 times our n value minus 1. So we're just doubling our n value and we're subtracting 1 from it. Let's do one that's slightly trickier. Let's try something like number 2 here. Go ahead and pause the video and ask yourself, what am I doing to my n to get my a sub n? Well, hopefully you found that a sub n is simply our n value squared plus 1. I do want to kind of emphasize this right over here. Notice those kind of dots that we have, also known as ellipses, are to indicate that this is what we call an infinite sequence. These terms go on infinitely. So all the more reason to have a really helpful way of generating any possible term in that sequence. All right, now let's go the other way around. Now let's take a look at some sequence where you're given a sub n and you just want to generate a certain number of terms in the sequence. So this is not that different from just evaluating a function, right? So if I wanted to find a sub 1, this would be equal to negative 1 to the 1 power times x to the 1 plus 1 all over 1 plus 1. And this is our first time seeing something like this, factorial, right? So that exclamation point doesn't mean you're just yelling the number. It means it's a factorial. And so the way a factorial works, and let me just kind of quickly move over here and we'll come back to that problem. A factorial is the idea that we are multiplying that number by all of its previous positive integers. So for example, something like 3 factorial would be equal to 3 times 2 times 1. Now, by definition, we are going to say that 0 factorial is equal to 1. There are a lot of reasons for this, which I'm not going to get into right now, but just commit that to memory, that 0 factorial is equal to 1. And if you have questions why, feel free to just look it up or just ask me during our next class, and I'm more than happy to kind of give you a really easy breakdown for why 0 factorial is equal to 1. All right, so if we now know what a factorial is, we can then simplify this here. We have negative 1 to the 1, so that's going to make this term negative. Well, we should actually see what's happening in the next term. This is x to the 1 plus 1, that's x squared. So I'm just going to write our numerator as negative x squared. All of this over 2 factorial. So 2 factorial is just equal to 2, so I'm just going to leave that as it is, because 2 factorial is 2 times 1. So go ahead and pause right now and see if you can come up with the next 4 terms in the sequence. And if you did, hopefully you find that the sequence is written out as the following. And we're going to box that. I want to also highlight here that these terms are alternating in sign. The first term is negative, the next term is positive, the next term after that is negative. This is what we know. This is what we call an alternating series because it's alternating in signs. Also note the way that I've written out my sequence. I'm writing them in order with commas just to separate the terms so things don't get muddied together. Okay. So now that we've had a chance to kind of work through factorials and understand that it's that number times all of its previous positive integers, let's practice simplifying with factorials. So let's try these examples here. So what would 6 factorial over 4 factorial look like? Now this would be incredibly annoying to do if we had to evaluate what 6 factorial was, evaluate what 4 factorial was, and do some math to try to simplify or divide those terms or values. But instead, let's try to kind of leverage what actually factorials are saying to our benefit here. What is 6 factorial? Well, 6 factorial is the same idea of 6 times 5 times 4 times 3 times 2 times 1. Now, think for a second here. What is all of this equivalent to? All of this is just simply 4 factorial. Well, so if that's the case, I can actually rewrite my numerator as the following. I can actually say that this is equal to 6 times 5 times 4 factorial. Well, if you have a 4 factorial in the numerator and a 4 factorial in the denominator, we can just divide these out. What are we left with? Just 6 times 5, which is 30. So much easier. Now, what if we were to do something like this with the variables or the n values instead of actual real numbers? Well, the answer is actually something really similar. What does n plus 2 factorial look like? Well, it's n plus 2 times its previous term. Well, what's n plus 2 minus 1? Well, it's just n plus 1. So this is n plus 1. Well, what's n plus 1 minus 1? It would just be n. Well, what's n minus 1? n minus 1. Then n minus 2, and so on. And this is going to go on infinitely here because we're not dealing with actual real numbers. We're dealing with variables. So in this form, this is going to go on infinitely. But think about this for a second. Remember what we're trying to do. We're trying to simplify this with n factorial. So what is this equivalent to? Kind of the same idea. This is n factorial. All of this is n factorial. So I'm going to rewrite that as such. Let me clean that up as well. So all of this is just n factorial. And again, I can divide these out. So what are we left with? N plus 2 times n plus 1. And you can multiply these out if you want. Those are equivalent. So if we actually compare these side by side, we're seeing that these are we're doing exactly the same thing, right? We're doing exactly the same thing. So try number 3 now. Something slightly different going on in number 3, but I encourage you to pause the video and try to simplify number 3. Welcome back. Let's try to go over number 3 together. And I'm hoping that if you found that by trying to expand out the numerator, we kind of end up in a place where we're not getting any closer to simplifying. Because the numerator expanded out is 2n minus 1 2n minus 2, 2n minus 3, and this is going to keep on going. That doesn't help us at all. That's never going to be able to simplify. And it's because we're expanding the wrong part of our ratio here. Because we're looking at this, which is greater, 2n minus 1 factorial, 2n plus 2 factorial, the denominator is greater, so it doesn't actually make sense to expand out our numerator. That's kind of like if we had 4 factorial over 6 factorial. Expanding out the numerator here doesn't actually help us divide out into our denominator. We'd actually want to do the following. We actually want to expand out the denominator so that we can divide these out. So for that same reason, that's what we're going to do here with our ratio here. We're going to write this as 2n minus 1 factorial. And in our denominator, this is 2n plus 2, 2n plus 1, 2n. And I'm going to actually probably need some more space to work with here. And then 2n minus 1 factorial. And there it is. That's what we're ultimately looking for, a common factorial that we can divide out from both the numerator and the denominator. So what we're left with is just 1 over all of this. And if you want to leave that in the form, that's totally fine. Okay. Let me talk about one specific type of sequence before we look at series in our next lesson. And that's what's called a recursive sequence. And a recursive sequence just simply means that each term depends on the previous term. We have to know what the previous term is in order for us to get our next term. So for example, let's take a look at this particular recursive sequence. We're told that the first term is 6. And every term, the fact that we're using k here, don't let that confuse you. It's the same idea of whether or not we use k or n. So a sub k is simply 2 times, this is just a fancy mathematical way of saying the previous term. K minus 1 means the previous term, right? K plus 1 would be the next term. K minus 1 is the previous term. So we're going to do 2 times the previous term, and that entire product minus 3. So a sub 2, for example, would be 2 times a sub 1, our previous term, minus 3, which is 2 times 6 minus 3, and that's equal to 9. Well, what's a sub 3? It's 2 times a sub 2 minus 3. It's 2 times 9 minus 3. And let's just keep on going. A sub 4 then would be equal to, I never finished simplifying that. That would be 15. A sub 4 would then be 2 times 15 minus 3, which is 27. And a sub 5 is equal to 2 times 27 minus 3, which is equal to 51. So I'm going to write out my answer as a sequence, as a good mathematician should. And there it is. There's our sequence here. Okay. Now I'm going to just move that here so we can try number 2. Okay. Go ahead and try number 2 now. What would this sequence be? Well, let's go ahead and talk this one out. Well, we know that our first term of our sequence is 1. But the next term of our sequence is also 1, which is kind of strange. And we're told that our a sub k rule is, again, our previous term plus that term's previous term. So in other words, it's the sum of the 2 previous terms. So a sub 3 is equal to a sub 1 plus a sub 2. In this case, 1 plus 1. That's equal to 2. A sub 4 is equal to 2 plus the previous term, 1 plus 2, which is equal to 3. A sub 5 is equal to the sum of these 2 terms, 2 plus 3. Well, that's just equal to 5. And if I were to write these out, does this look familiar to you? And if you said the Fibonacci sequence, you would absolutely be right. Okay, this is what we call the Fibonacci sequence. Okay, so hopefully that gives you a good sense of what a sequence is and our first kind of example of a unique type of sequence. Next, let's actually look at series and summation notation.